Visible lecture 19 Kappa's course.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, let's begin. And as you know, we have been discussing inter-annotator agreement. We have to take inter-annotator agreement very seriously, especially in the context of our lab 2. I'll spend some time today on discussing problems and situations where we have to take inter-annotator agreement quite seriously. And the inter-annotator agreement is expressed by what are called Kappa scores. And in the last lecture, we saw there is a connection between Cohen Kappa, precision, recall, F score, true positive, false positive, and so on. We'll go back to that discussion again. And the interesting thing is that for last 1 year or so, the discussion that we are having on hypothesis testing has bearing on Kappa score also. So what is the relationship between hypothesis testing and Kappa score? We would like to remark on that too. But a major part of the lecture today will be discussing inter-annotator agreement situations in the context of projects in our lab so that you can relate to these discussions. So just to remind you that precision and recall can be very easily understood in terms of a Venn diagram where there are two sets. The set S1 is the obtained set through a machine learning model, and S2 is the actual set of instances. So it is the actual set of dogs, and S1 is the hypothesized set of dogs. So the square indicates universe, and every point in it is the whole universal space, constitutes the whole universal space. We can look upon the square box as animals. So the universe is decided depending on our decision to which part of the conceptual space we want to focus on. So S1 is the obtained hypothesis set. S2 is the actual hypothesis actual set, and S1 intersection is intersection S2 is called the true positive. And everything outside of S1 and S2 is the true negative, where there is agreement between S1 and S2 about the negative set, negative instances. And the intersection is also the agreement region between S1 and S2. The set of false positives is S1 minus S1 intersection S2. So this black half moon is the set of false positives, because S1 thinks it is a positive set, but actually it is outside this red circle. So these are not positive instances. They are thought to be positive, so it is false positive. Similarly, S1 excludes this half moon of red color. So this is the false negative set. They should have been included in the conceptual space. So precision recall, we know, can be very easily computed from S1 intersection S2 divided by S1, which is precision. That is, denominator is the obtained hypothesis set, and recall is S1 intersection S2 divided by S2. So denominator is the actual set. So in terms of contingency tables also, this can be understood. So actual is on the rows. The ESS are A and B. So A plus B is total number of ESS as per actual conceptual space. No is C plus D. And obtained is A plus C, and no is B plus D. So A is the intersection set, the number of elements in the intersection set. B is false negative, C is false positive, and D is true negative. Okay, so we can also discuss this in terms of the contingency table. Contingency table is a nice instrument to discuss agreement between actual and obtained, which is also the confusion matrix. Okay, the contingency table in this case where the actual conceptual space is compared with the obtained conceptual space. Okay, this is forming the confusion matrix, or used in this situation as the confusion matrix. The contingency table in this case is called confusion matrix. So in terms of true positive, true negative, false positive, false negative, we can see that P is actual intersection obtained, which is A, divided by the actual divided by obtained, which is A plus C, which is A plus C. So this is true positive by true positive plus false positive. Recall is actual intersection obtained, which is A, divided by actual ESS, which is A plus B, and that is true positive by true positive plus false negative. So we can relate all this to Cohen-Kappa 2. And Cohen-Kappa, you remember, is nothing but the subtraction of PO and PE divided by 1 minus P, where PO is the probability of observed agreement. So there are 19 instances in this example. 10 are yes agreement, 2 are no agreement. So 10 plus 2 is 12. 12 by 19 is 0.63. And we have remarked before that probability of observed agreement can be misleading. 0.63 is reasonably high agreement between A1 and A2. But as the psychologist Cohen pointed out in 50s, that you have to subtract the influence of completely chance agreement. And we discussed a peculiar situation where A1 and A2 have no idea about the problem at hand, and they simply randomly give yes and no. And then the probability of this chance agreement can be computed as 13 by 19. This is number of times A1 says yes out of 19, into 14 by 19, which is number of times A2 says yes. Okay, this is 14 out of 19, plus number of times A1 says no, divided by 19, into number of times A2 says no, divided by 19, which is 0.58. Okay, so this 0.58 is the probability of chance agreement, and this PE is subtracted from PO, 0.63 minus 0.58. PO value can be at most 1. The highest value of PO is 1. That will happen if these cross diagonal elements are 0. Okay, so PO minus PE and divided by 1 minus P will in this case give 0.12. The probability of chance agreement being pretty high reduces the Cohen-Kappa value quite drastically, 0.63 to 0.12. Now, I was mentioning, where does hypothesis testing and inter-rotator agreement interact? Okay, how do they interact with each other? So we obtained this Kappa score, okay, 0.12, and the probability of chance agreement is 0.58. Okay, so this difference that we have obtained between probability of chance agreement, okay, and this Kappa score, this quantity 0.58 and 0.12, okay, this difference, is it statistically significant? Okay, the Kappa score is a measure of agreement between two raters or two annotators. The probability of chance agreement is another measure of agreement between A1 and A2, okay, by chance. So how far should the Kappa score be from this probability of chance agreement to be believable? Okay, so that that difference should be statistically significant. Statistically significant means this should recur, and this should be the case in many such example situations. Then we can begin to believe this Kappa score. So this difference is should be statistically significant. That is where hypothesis testing and inter-annotator agreement interact. Okay, and as you know, in hypothesis testing, we'll have to start with null hypothesis. The null hypothesis is that A1 and A2 completely independently of each other give their ratings. Okay, and their agreement or disagreement is purely by chance. That would be the null hypothesis. And with respect to that, we'll have to do test of significance. So that is another discussion which we'll come to. Okay, but we should always remember this correction factor, which was introduced by Cohen as minus P in both denominator and numerator. So 1 minus PE is like a normalizing quantity. So you should think about why this 1 minus PE is a normalizing factor, and we should take it up for discussion at some point of time. Why this normalization is necessary, for example. Okay, so this reduces the influence of number of data points and the difference of values between the data points. Okay, all these are taken care of by this normalizing factor. Let's proceed. Now, we can also relate to Cohen Kappa to precision, recall, and so on. An interesting formula for Cohen Kappa, which I would like you to remember, is that Cohen Kappa is equal to 2 into agreed yes into agreed no minus disagreed yes into disagreed no divided by obtained y into actual no plus actual y into obtained no. Okay, so there is a kind of symmetry in this formula, which is 2 into the agreement situation minus disagreement situation, and then there is a cross action between actual no, actual yes, and obtained no. Okay, so this is an interesting formula which is obtained from this consideration of true positive, true negative. So I'd request Apurva to start recording. Okay. Oh, it is being recorded. Okay. Okay. So now we proceed, and we would like to remember that good Cohen Kappa score is from 0.8 upwards. Okay. So 0.4 to about 0.6 is weak, 0.6 to 0.8 is moderate, 0.8 to 0.9 is strong, and above 0.9 is almost perfect. And this also relates to the percentage of data that we can rely on. So, weak Kappa, in this case, you can rely 15 to 35% of the data. And moderate Kappa, 35 to 63% of data. Strong Kappa, 64 to 81%. And above 90, almost perfect. And I can rely on 80 to 200% data. So what is this reliability score? How do we know that Cohen Kappa 0.4 to 0.6 allows me to trust 15 to 35% of the data? Okay, that is an interesting discussion which we need to take up. And after all, what is the use of Cohen Kappa? The use of Cohen Kappa will give me the interannotated agreement. But what of it? Okay, why should that be important for me? The importance lies in this third row. How much of this annotated data I can rely? Okay, if I cannot rely on the annotated data, I cannot rely on my machine learning model also. Okay, the machine learning model is as good as the data on which it is trained. So Cohen Kappa is a good indication of the reliability of the annotated data. Reliability of the annotated data which is fed into the machine learning model. There are some comments on the chat box. I'll take it up after some time. Okay, so let's remember that moderate Cohen Kappa starts from 0.6, okay, and its strength increases from 0.6 to 1. So the desirable Cohen Kappa starts from 0.6. Okay, desirable Cohen Kappa starts from 0.6. Let us remember this, and that is when we can trust about 40% of the data, let's say. Okay, so now we come to Flies Kappa, which is in our attention now, and I would like to give you solid examples of Flies Kappa usage in the context of projects going on in our lab. So this example is very frequently used in many YouTube videos also, you will see. This is from the Wikipedia, which gives a nice description of what is Flies Kappa. And Flies Kappa paper also came up in 1950 to 60 range. After some time, Cohen wrote his paper. And interestingly, Flies also was a psychologist. Okay, he generalized to multiple categories and multiple annotators who give annotation on the data. Cohen Kappa is for two classes, remember. There could be, so for Cohen Kappa is for, yes, multiple classes, but only two raters. But when you have more than two raters, then we have to make use of Flies Kappa, Kendall Tau, and so on. So here is the example situation. There are 14 raters. Remember the notation. Small n indicates the number of raters. And they assign 10 subjects, that is 10 data instances. And the data instances are given the notation capital N. Remember this. And the number of categories is K. Okay. So there are 5 categories. 10 data points called subjects and 14 raters. Small n, number of raters. Capital N, the number of data points or subjects. K, number of categories or number of classes. So categories are depicted in the columns and subjects or data points on the rows. So each cell lists the number of raters who assigned the indicated subject to the indicated category. So cells in Flies table record the raters, while those in Cohen table record data points. Okay, we'll compare and contrast Flies and Cohen. So here is the example. Let's look at the table carefully. So the number of data points is 10. Okay, data points, remember, were called subjects by Flies, and that terminology carried forward. So 1, 2, 3 up to 10. And the number of categories is 5. 1, 2, 3, 4, 5. Now, if I take data point number 1, subject number 1, then all 14 raters are giving data point 1 the category of 5. Okay. If I take data instance 2, then nobody is giving the rate, placing the data point in category 1, but two raters are placing it in 2, 6 in 3, 4 in 4, 2 in 5. The sum should be equal to 14. 6 plus 4, 10, 10 plus 2 plus 2, 14. Okay. Similarly, if I take data point number 10, then nobody is giving it a rating of category 1. The maximum number of raters are placing the data point in category 5. Okay, and that number is 7. Again, the sum of these row values should be equal to 14. Okay, so each cell tells me for that particular data point how many raters have placed the data point in the corresponding category. Okay, this is the meaning of the table for Flies Kappa computation. Now, if you compare this with Cohen Kappa, then Cohen will have only 2 raters, and we do not have a table where which is data points versus categories. No, we don't have. Okay. Instead, we have the table as rater number 1 versus rater number 2. Okay, the table is with respect to rater number 1 and rater number 2, whereas Flies Kappa table is subjects versus categories, data instances versus classes. Okay, this is how the table is organized. And what is the raw data? What does each cell contain? Each cell contains the number of raters who have placed this particular data point in the particular category indicated by the column and data point indicated by the row. Okay, so you can of course sum up the totals under every column. You can sum up the totals under every row, and they have their interpretation. So in the category number 5 appears 32 times in the annotation. Okay, category number 4 appears 21 times, 3 39 times, and so on. Okay, so when you sum these things up, then you will have the quantity as total number of times the category versus subject has appeared in the data. Okay, so we'll look at this computation as we go forward. Now, the table for Cohen-Kappa is for A1 versus A2 and the total number of times they have said yes or no, or class 1 and class 2. Okay, now comparing Flies and Cohen-Kappa, the cells in Flies table record the number of raters, while those in Cohen table record the number of data points. Okay, in Flies table, we record the number of raters, while those in Cohen table record the number of data points. How many yeses, how many nos, and so on. Cohen is more gross in the sense that the number of agreements is not recorded for each data point, but overall numbers are recorded. Okay, so from Flies table, okay, if there are two raters, from Flies, two raters in two categories, then from Flies table, you will be able to construct the Cohen table. Okay, but not vice versa. From Cohen table, you will not be able to obtain the Flies table. Okay, because Flies table looks at every data point, and for every category for the data point puts down a number, which is the number of raters who have put this data point in that particular category. Flies records the number of raters in agreement per data point per category. Okay, so this is a more, it is a finer view of the data compared to Cohen's table. Okay, now we take up some practical situations, which okay, I can see some questions on the chat box. I'll come to that. Now we'll take some practical situations. Machine translation evaluation is a very important inter-annotator agreement situation. Okay, machine translation output is given adequacy and fluency ratings. More about it as we go forward. And e-commerce user rating of services. Okay, so each instance of the service is a subject, customers are raters. Course evaluation of a faculty member, this I had mentioned before, and there are more examples. So let me spend some time on why we take inter-annotator agreements so seriously in our lab. So we have this IIT Bombay English Marathi machine translation system, and the evaluation has been done by CDAC outside of IIT Bombay. So for tourism domain, 1,000 sentences were taken from various state government tourism websites. And for law domain, NPTEL law courses were taken. I don't remember the number of sentences under law. And subdomains are agreements, contracts, constitution, acts, law, RTI, grievance, and so on. So this is the evaluation situation which CDAC has set up for IIT Bombay. We did not give them those sentences. They collected it from different websites for tourism domain and law domain. Okay, this is an independent evaluation. Now, what are the categories and what is their semantics? So if the grade is 0, then there is no output coming from the machine translation system. Or if it is written as this is not translated in the target language, or input is something else and output is of some other sentence. Okay, this is applicable for open testing. So either no output or no relationship between input and output, the source sentence and the target sentence, or sometimes the output comes as not translated. So grade 1 is nonsense. If the sentence doesn't make any sense at all, it is like someone speaking to you in a language you don't know. Okay. Category number 2 is some parts make sense, but is not comprehensible overall. For example, listening to a language which has lots of borrowed words from your language, you understand those words, but nothing more. Only the words are understandable, not the combination of the words in the sentence. 3 is comprehensible, but has quite a few errors. For example, someone who can speak your language, but would make lots of errors. However, you can make sense out of what is being said. Okay, you can get a motamoti idea of what is said. 4 is comprehensible occasional errors. For example, someone speaking Hindi getting all its genders wrong. Okay, so Sita khata hai, Ram khata hai, that kind of situation. 5 is perfect. Okay, someone who knows the language. So these are 5 categories going from 0 up to 5. So again, very quickly: 0, no output; 1, nonsense; 2, some parts make sense; 3, comprehensible but has quite a few errors; 4, comprehensible occasional errors; 5, perfect. Okay, these are the 5 categories. Now, what the annotators do, or the evaluators do, is that they do 2 kinds of testing: comprehensibility and fluency. Comprehensibility means, does the output sentence carry the meaning contained in the source sentence, and is the sentence understandable overall? Okay, and then under that again there are 2 situations: blind and open. The evaluator doesn't see the source sentence. Okay, and in open, the evaluator sees the source sentence. And the evaluator is supposed to be bilingual. If it is English Marathi, the evaluator should understand both English and Marathi. Now, when the evaluator is able to look at the source sentence, the expectation becomes higher, right? The meaning is in front of the evaluator. Now, if the target sentence or the translated sentence is not properly conveying the meaning, then the rating would fall. Maybe only part of the meaning is conveyed. In case of blind testing, the fact that only part of the meaning is conveyed is not known because the source sentence is not in front of the evaluator. So naturally, in blind testing, the comprehensibility score is higher typically than the open testing. Okay, so in tourism domain, we have 92.46, which falls to 84.07 from blind to open testing. Law domain, 97.70 and goes to 91.30. Okay, falls to 91.30. But overall, the values are pretty good. That means in tourism and law domain, we are able to translate pretty well as far as comprehensibility of the output is concerned. But comprehensibility is not enough. Okay, the users of language get put off if the sentences are not well formed, sentence after sentence. If the fluency is not maintained, the language users become they get put off actually. Yeah, and fluency is typically affected in the function words, that is in prepositions, conjunctions, in the agreement, in the gender marking, in morphology. Okay, that is where fluency gets affected. Again, here you can have blind testing and open testing. Now, this is an interesting situation. Fluency value is much lower than comprehensibility. So that means the machine translation output overall does not have very good well-formedness as far as the output sentence is concerned. And it is also interesting to see why in blind testing, again, the score is higher than in open testing. So what happens is that probably some preposition phrase hasn't appeared in the output sentence. Some preposition phrase has not appeared in the output sentence, but the sentence looks good still. Okay, it still looks good. But the preposition attachment has not happened. So the moment you see the source sentence, you can you spot that yes, a preposition phrase is missing. Then you penalize the fluency. Okay, so that's why in open testing again, the fluency value also gets penalized if you get to see the source sentence. But you can see that for our English Marathi system, machine translation system, as far as test report from CDAC is concerned, we are doing pretty well on the comprehensibility and reasonably well on the fluency part, but could have been much better. By the way, ensuring fluency is a harder problem than ensuring comprehensibility. Okay, this as an aside, I'm making this remark. When you compute the blue score, you take blue 1, blue 2 up to blue 4, and higher n-grams. Blue 4, for example, focuses on syntax, on the fluency. And blue 1 score focuses on lexicon, that is the word match. And so lower blue score addresses comprehensibility, lower n-gram blue score addresses comprehensibility, higher n-gram blue score addresses fluency. Okay, and getting higher n-grams correct. Okay, as the length of n increases, the probability of getting exact match reduces, right? You will agree with me. As n increases, the sequence of n words, okay, getting that match exactly with respect to the reference sentence, that probability would decrease, right? So that's why getting fluency agreement with the reference sentence is more difficult than getting adequacy agreement or comprehensibility agreement with the reference sentence. This is how language operates. Okay, so so this also tells us uh, uh, why it takes time to be able to produce fluent sentences. Okay, we need to mature. The age has to increase to be able to form well constructed sentences. Fluency is not easy to obtain. If you observe a child and the way the child acquires language, you will see that initially the child produces one word, then maybe 2-3 word phrases, then sentences which are not really well formed, जिसको हिंदी में टूटा फूटा बोलते हैं, टूटा फूटा sentences are constructed, and it takes time. Maybe at the age of 25-30, you begin to produce really native speaker acceptable sentences 80%, 90% of time. Of course, there are people who are born with very good language ability, but in general, on an average, we see that it takes time to mature in the linguistic output. Linguistic proficiency matures with age. Okay, maybe not so in terms of mathematical and algorithmic abilities. Okay, and programming abilities. So if you, this is a digression, but our lectures are not really for covering a course. These are entertainment lectures, academic entertainment lectures. So we can digress a bit. So if you take many different kinds of skill, mathematical skill, programming skill, language skill, okay, then there are some skills which take time to get established in our body and mind. Okay, so sporting skills, for example, physical skills, they some of them are for lower age, some of them are for higher age. Linguistic ability takes time to establish. Okay, this is a well documented fact. But mathematical and programming skills, most probably, they get developed at a much earlier age. Algorithmic skills and mathematical skills. Okay, so this is an interesting discussion which we need to take up at some point of time. So these are graphical representations. Now we come to another interesting discussion with respect to lengthwise values. So you can see that when the sentence length is small, for short sentences, the comprehensibility value is high, 95.91. Okay, and fluency value is also high. But as the length increases, both comprehensibility and fluency begins to fall. Similarly, for tourism too, comprehensibility and fluency begin to fall as the length of the sentences increases. And that is expected. As the length of the sentence increases, you have to manage more language material, and you have to place them properly, order them properly. This is more work. So both comprehensibility and fluency reduces. And what all this is with respect to the output that is obtained from the machine translation system. Now, now we come to this point of evaluator or annotator agreement. So in this case, the annotators are evaluators. So the interesting thing was, when there are 5 categories, then the Fly's Kappa score for law was 0.3. For tourism, it was 0.37. For law and tourism, the Fly's Kappa score increased to 0.43 and 0.51 when we combine grade 0 and 1. Grade 0 was no output and 1 was nonsense. Okay, so we combined these grade 0 and grade 1. A much more desirable combination was combining grade 2 and 3. So grade 2 and 3, you'll recall, are the following. 2 is some parts make sense, and 3 is comprehensible, but has quite a few errors. Okay, so the evaluators became quite confused as to where to put the sentence with respect to its grade 2 and 3. Okay, so they were not able to make this fine distinction between 2 and 3, and 0 and 1 also. 0 is not only no output, but also other problems with the output. Okay, no relationship between source and target, for example. So we decided to merge 0 and 1 and 2 and 3, and then see what happens to the Fly's Kappa score. 4 and 5, of course, were not touched. So there we saw that the Fly's Kappa score increased as per expectation, increased from 0.3 to 0.43 in law and 0.37 to 0.51 in tourism. So these Fly's Kappa scores of 0.43, 0.51, etc. are very good. Okay, in fact, 0.51 is very good. Unlike in Cohen Kappa. In Cohen Kappa, we begin to accept the Kappa score from 0.6 upwards. Okay, but not so for Fly's Kappa, that we will very soon see in terms of a qualitative table. But notice this point. The Fly's Kappa score increases when we merge categories. Okay, so as the number of classes reduces, the categorization becomes more and more coarse. Okay, this fine distinction or discrimination between different categories reduces, and that reduces the cognitive load on the annotators or the evaluators. Okay, so when we take a very elaborate annotation framework, then the annotation is very fine grained, no doubt, of very rich quality, no doubt. But then this is more cognitive load on the annotators, and annotators would tend to disagree more. Okay, disagree more, and they are also likely to make more mistakes. So by merging of categories, we reduce that possibility of disagreement. Whether it is good or bad, it depends on the problem. But annotation guideline or designing the annotation framework is an exercise in trade-off. Okay, too many annotation levels, more possibility of disagreement and mistake. Too few, not very useful in the downstream application. That annotated data doesn't have much value. The richness is very minimal. Okay, so this is what we did, and the annotation scores were recorded. So this was one situation where we had to worry about Fly's Kappa, inter-annotator agreement, and so on. Another situation is movie rating. So if you go to IMDb, which is where a lot of moviegoers give their views about a movie. So there is this movie which came out in Sherni, Vidya Balan being the protagonist. She goes to a village to track and capture a tigress, which was creating havoc in that village. So this movie is called Sherni, and its rating is obtained from user views. So here you can see that there are 10 stars, and the user has chosen to give 9 stars to this particular movie. Now 10 stars, which means there are 10 categories. Okay, 10 stars, 1, 2, 3 up to 10. Okay, and there can be also no star. Therefore, there will be 11 categories, and 11 categories is a fairly complex classification situation, pretty fine grained. Okay, how do you distinguish between 8 and 9? Not easy. If you had, on the other hand, 0, 1, 2 up to 4, then this would be more tractable. But this is the situation. The users give their reviews in terms of number of stars, and these stars correspond to different categories. So, okay, just a second. Oops. Oh, I went to the end of the presentation. Oops, sorry. Yeah. Okay. So this is another situation where you get user reviews on e-commerce companies or movies, services, and so on. So the third situation for us is the project on script debiasing. We are working with Accenture for this problem, and the goal is to find out if a movie script or drama script or a play has any kind of bias in it. So our these slides are from the debias team's work, which consists of Nitish, Sandhya, Nihar, Prapti, and Himanshu. So here again, the annotation situation is complex. Given a movie script, we should identify if there is bias and what type of bias is present. And we have decided to identify from the following categories of bias: gender, occupation, race, religion, ageism, LGBTQ. So there are 6 categories. By the way, is my slide visible? It's called problem definition for bias.
Yes, sir.
Yeah.
Yes, sir.
Okay. Yeah. Okay. And the situation can be quite complex and fine. So because of all these biases can have subcategories. So gender can have alpha, beta, and sexism as 3 different categories. So for example, the men exchange uneasy looks. Why is Connie in men's business? Confining the space and position of a woman in male-dominated arena. So if you look at this data, this particular sentence is, it smells of bias. Why is Connie in men's business? So Connie is presumably the name of a woman. And why is she in men's business? So this is a loaded or bias statement. Okay. Alpha, beta, sexism, etc. These are for later discussion. In occupation, you can have bias, and there are 3 kinds of bias: economic, administrative, and societal perception. So, for example, in economic, there is a character called Stern who is saying the standard SS rate for Jewish skilled labor is 7 marks a day, 5 for unskilled and women. Okay, so there is a bias here because Jewish skilled labor is the target. Okay, with respect to occupation and race. So there is race and occupation bias here. Societal perception, Schindler, because I said I would. What you want a contract to be filled where? He slips into the code. I said what I'll do. That is our contract. Jew investors. So, so these kind of statements appear in movie scripts, and the censor board can catch the producer, the director, etc. if this kind of bias is rampant and has the potential of inciting some kind of social unrest, protest, etc. Okay, which can jeopardize the social political stability. So censor board is careful about detecting biases, and movie makers these days particularly are becoming sensitive to this particular problem. So we have started working on this with Accenture. Then there can be race bias, which has sub-biases like dialect, color, appearance, regional, societal perception. Regional, he is not a southerner and speaks with articulation and intelligence. See the loaded statement. He is not a southerner and speaks with articulation and intelligence. So articulation and intelligence are good signs of speech, and that as if is not given to a southerner. Okay, so there is a bias against southerner saying that they cannot speak with articulation and intelligence. So there is a bias. Okay, then you can have ageism, societal perception, physical behaviorism. An old woman past 80, withered, still regal with a green turban around her bald head, is propped by pillows, her blue eyes looking out at us from her bed. So the reason that it has bias is that terms like withered, bald head refers to physical aspect of age. Okay, societal person beside him is a rough-hewn, charismatic man despite his 59 years. Despite his 59 years, as if at the age of 59, a person cannot be charismatic. So the word despite introduces some semblance of bias. So this kind of fine language sensitivity is required to see this. And then there are LGBTQ biases and so on. So there are 6 categories And if you go to subcategories, there may be 20, 25 subcategories. And when the annotators sit down with the data and decide how to give these bias annotations, bias labels, it can become quite a challenging task. Okay, now if we keep the categories as only 6: gender, occupation, race, religion, ageism, and LGBTQ, then it is manageable. But the problem is that this is an interesting situation of multi-levels. A sentence can have multiple bias. Okay, so this is one problem that we are facing and discussing as to how to tackle the problem. And of course, machine learning has discussed such problems before. So similarly, we are also discussing offensive text or toxic text in the context of bias, where again the annotation categories could be non-offensive, offensive, targeted insult and threats, untargeted, individual or group. Okay, so in many different ways you can categorize data. Okay, data can be categorized in many different ways, and this categorization should be valid. I should be able to trust the data to feed into my machine learning model. Okay, so this is an example of multi-level data. Top sergeant, assuming liberals are unarmed, would be a grave mistake by the deplorables. This is offensive, targeted insult, and is targeted to a group. So this data has multiple levels. Okay, and imagine two annotators annotating. They may give they may give less than the actual number of levels or more than the actual number of levels, and there the agreement becomes a very important concern. So we go back to now flies Kappa and its maths and so on. Okay, so we'll finish in 5 minutes and then go to chat box comments. There are quite a few comments, looks like. So back to flies Kappa. N is the total number of subjects. Small n is the number of ratings per subject. K is the number of categories into which assignments are made. Subjects are indexed by I. Categories are indexed by J. I varies from 1 to N. J varies from 1 to K. Nij represents the number of raters who assign the ith subject to the jth category. And now here are the important formulae. Small pj is 1 by n into n sigma j equal to 1 to capital N nij. Okay, so what is J? J is over the categories. So go over the columns across a row. So note all the different categories and subject combinations. Sum them up. Sorry, J goes from 1 to n. So this is over the subjects. Okay, this is down the column. So get sigma nij divided by capital N into small n. And you can see that sigma j equal to 1 to k, pj should be equal to 1. Okay, then capital Pi is 1 by n into n minus 1, j equal to 1 to k, nij minus 1. So this, when you do the algebraic manipulations, then this becomes 1 by n into n minus 1, sigma j equal to 1 to k, nij square minus n. And then PO, the probability of agreement is 1 by n into sigma equal to 1 to n pi. PE, the probability of chance agreement, is j equal to 1 to k pj square. And kappa, as before, is calculated as PO minus PE by 1 minus PE. The things to do here are, why is PO equal to 1 when there is complete agreement? So in the flies kappa table, if each cell has, if the table is such that in every row, only one cell has all the annotators, then this PO value will be equal to 1. So for every data point, there is complete agreement between the raters. Then PO will be equal to 1. Try to prove it yourself, or we will do it in the next class. Okay, and 1 minus P, as like Cohen kappa, is the normalizing factor. PE is the correction factor, the probability of chance agreement. Now, why does the chance agreement get computed this way? That pj square, j equal to 1 to k, pj is 1 by n into n, j equal to 1 to n, nij. Why is it calculated this way? We have to understand them in more detail. So when we do this computation, we form these capital PIs, which are sum of rows, okay, which are row operations, and then small pj's, which are column operations. So from these, we can obtain, for example, P1, small p1. Small p1 is this column, which comes out to be 0.143. How does it come out to be 0.143? You take the sums and divide them by, take these values, sum them up, and divide them by capital N into small n, number of raters into number of data points. So this is equal to 0.143. The row value is computed as follows. P2, for example, for the second row, which is coming out to 0.253. How is this done? 0 square plus 2 square plus 6 square. So there are 5 categories. So square of each nij minus total number of annotators, which is 14, divided by total number of annotators into total number of annotators minus 1. So this comes out to 0.253. Now, when you sum these PIs, okay, then you get 3.780. PO, the probability of agreement is 3.78 by 10, 0.378. So 10 is the total number of subjects, okay? And then PE is coming out to 0.213. Now Kappa is 0.378 minus 0.213 divided by 1 minus 0.213. 0.210 is the Fly's Kappa value. What is the theoretical basis of this? We will start this discussion today, but we'll complete in the next class. And how good is this Kappa score? We see that Kappa is much more refined than Cohen, okay, multi-class, multi-raters. So Kappa says 0.2 is fair agreement. And Cohen Kappa says 0.6 is moderate value. Okay, so Kappa begins from 0.2 as fair, goes up to moderate, substantial, and almost perfect, through 0.2 to 0.4 to 0.6 to 0.8. Okay, so lower Kappa value for flies is expected compared to Cohen. Okay, so when we have a Cohen flies Kappa value of 0.3 or 0.4, this is fairly good. Okay, and that is bad for Cohen Kappa. Now, if we take a deeper look into flies, then these are the formulae, and here are the interpretations. Small pj is the proportion of all assignments which were to the jth category. So pj is proportion of all assignments which were to the jth category. So this is on the column. Capital Pi is the extent to which raters agree for the ith subject. That is, compute how many rater-rater pairs are in agreement relative to the number of all possible rater-rater pairs. All possible rater-rater pairs is n into n minus 1. Okay, relative to means you have to take a ratio. And extent to which raters agree for the ith subject, that you have to compute by taking the row sum. PO is the mean of PIs, and P is the probability of chance agreement. Okay, so these things we have to establish by looking at the formula. In particular, try to prove that the maximum value of PO can be 1. Okay, so these things we'll do. And the summary of today's lecture is that we have to take inter-annotator agreement seriously in the context of many problems where there are multiple annotators, multiple categories, and you have to trust the annotated data so that the machine learning model is trustable. Okay, so let me now go to the chat box. Okay, from Aman. Sir, generally, what is the difference between contingency table and confusion matrix? Okay, confusion matrix is done to compare actual values with obtained values. Okay, the output of the machine learning model with the actual values. That is the name given to confusion matrix. So confusion matrix is a special kind of contingency table. For contingency table, you have the row dedicated to one of the raters, the column dedicated to another rater. Now, if you look upon one rater as the actual human decision and another rater as the machine learning model's decision, then we should call it the confusion matrix. So confusion matrix is a special kind of contingency table. The raters here are machine learning model and the human beings. And in case of general contingency table, it can be two raters, two different raters. Okay, then is there an association, a common association between kappa score and p-value? Apparently, both of them are on strength of identified hypothesis. Okay, so this will take up in more detail when we see the confidence in the kappa score value, when we discuss the confidence in kappa score value. How significant is the kappa score value with respect to the random chance agreement? Okay, so this is a test of significance. And then we'll have to take up this question. But roughly, what is p-value? P-value is if I take the Z table, then we know that for 95% confidence interval, okay, the rejection region is between less than minus 1.96 and plus greater than plus 1.96. Okay, if it is a symmetric situation. If it is greater than or less than, let's say if it is greater than, then the rejection region is from Z equal to 1.63 up to infinity. Okay. Now, suppose I say that I do not focus on rejection region, but I focus on the actual probability value that I obtain for the situation. Okay. So that actual probability value is the p-value. So one can give the probability of rejection, or one can give the p-value. Okay, so this point we have not covered so far, I agree. So apparently both of them are on the strength of the identified hypothesis. You're right. So how to relate all this, how to relate kappa score, p-value, etc. So I'll take a little more time to discuss this. Okay, then where does ground truth come in the flies table? So that's what Ritik is asking. And he is also asking, in the script debiasing project, does it consider intentional dialogues, like a character which is portrayed as, say, racist will obviously have a race bias? Yeah. So this is a point which we have discussed many times. Let me take up these questions one by one. Where does ground truth come in the flies table? What is the meaning of this question? Ritik, can you elaborate?
Sir, in case of Cohen's Kappa, we separate the portion which is the actual truth, the true value of data points and the annotated value of data point, isn't it?
So you mean the confusion matrix?
Of Cohen's Kappa.
Acha. So where does ground, no, what is the meaning of the question? Where does ground truth come?
Okay, sir, okay. Now I think I answered my own question. I was confusing that in Cohen's Kappa, it is like confusion matrix, and in confusion matrix we have the predicted truth and the ground truth. Doesn't have the ground truth. So ground truth doesn't come in either Cohen's table or in Fly's table.
Yeah, yeah. Ground truth doesn't come into play directly. Okay. Yeah. So if you, on the other hand, if you take one rater as the machine learning model, the other as the actual decision, then of course the actual decision side will give you the ground truth numbers. Okay. Yeah. Now, in the script debiasing project, does it consider intentional dialogue? So this is an interesting and important point, and we have discussed this also. So if the character is supposed to, convey bias, then you cannot say that the script has bias. Okay. So this is the offness, aboutness, which I mentioned to the debias team. So my favorite example there is that if the movie has a villain and the villain is portraying his character very well, then there will be many adjectives like horrible, defamable, okay, atrocious. Those adjectives will come. And if they're applied to the villain character, it is good. and that shows how effective the villain character is. And it contributes to the goodness of the movie. Okay, it contributes to the badness of the villain, but to the goodness of the movie. So this is the opinion about a character in the movie, and indirectly affecting the sentiment about the movie. So here also, if the character is supposed to have bias and that bias is projected very well, then that is a merit for the movie. Okay, so this we have discussed, and the annotators have to keep this distinction properly. Okay, maintain this distinction properly. Is the bias expected or is it not? Okay, so that's a good point. And then Sandhya says, if two annotators have given different levels to the data point, which level is considered for ground truth data? Oh, I see. This is the, I see. So what is, you're asking what is the, who amongst the two annotators is correct? Okay, so that is not known typically. Okay, that is not known typically. If I take a sentence and give part of speech tags, one annotator gives it noun. So golf, for example, golf club. So for golf club, golf, in the dictionary, golf is always shown as noun. So the annotator gives it as noun. But golf club, the club is qualified by golf. Some annotator would give it as adjective. Okay, so this dichotomy we have faced many times in pause tagging, pause tagging work. And here, is it noun or adjective? Both are correct from two different points of view. Okay, so that question is not really answerable easily. And Girish says we need annotations from at least two annotators to comment on quality of annotation. What if we have only one annotator? If is there any way to comment on such a case? Yes, unfortunately, this is a reality. Annotation is an expensive task. Hiring annotators is expensive. You have to pay money, and it takes time. It is an investment after all. So if only one annotator is annotating and we don't have more than one annotator, we have to go with whatever the annotator has done. We have to then rely on indirect and direct assessment, right? So we give it to the machine learning model and try the machine learning model on unseen situations and see how it performs. If it is not doing well, we have to suspect the data. Data is raw data. The annotation will then be questionable. Okay, yeah.
Sir, Kevin here. For both these last questions regarding this annotation, one thing we can also do is probably look up the crowdsourcing literature. So in case of crowdsourcing, where people like this clients are actually paying this crowd to get some work done, they often suffer from this problem that some people will just sign up for a task and give some random answers because they just want to get paid. Right. So that time, these people have to figure out that among the different participants, which of them were genuinely doing the task and which of them were just simply selecting some option randomly or something, right? So for that, one of the things that they typically do is they have some sort of similarity measure among different data points. And then they see that whether the annotator has given similar response for the similar data points. If there is very high discrepancy among the annotation for similar data points, then you can assume that the annotator is not good at this task. And that is how they eliminate those people from the data collection. So I guess this idea can also be extended to this scenarios discussed in the question.
Yeah. Yeah, so when the inter-annotator agreement is low, okay, if Cohen Kappa falls below 0.6 or Fleiss Kappa falls below 0.2, which is the region of fair annotation in two different cases, then we have to suspect at least two things. One is the competence of annotators. The second is the complexity of the annotation situation. If there are too many categories and the categories are not well separated, this will automatically bring down the Fleiss Kappa and Cohen Kappa score. And if the annotators are not competent, okay, that will show up in the form of random assignment to categories. And then the PE value, which is the correction factor, should go up. Yeah. And we have these probabilistic methods for computing the PE value, at least. Okay. Okay, so I think we'll end the lecture, but before we end, I'd like to say that for this semester, this is the last probability lecture. We'll resume these probability lectures from August again. When the semester begins, I'll notify to everybody when we restart these probability lectures. But we have finished 19 lectures. We'll go on for some time because this interaction of probability with AI, NLP, machine learning is a very, very rich discussion. And I'm finding that many things from statistics, probability are directly applicable to our problem, especially NLP, especially natural language processing. So I think it is worth spending time on these discussions. About 1 hour in every 15 days is not too much of an investment. And this should be useful to us. Okay, thank you. We'll meet for the information extraction work update meeting at 11. Oh, it is 11:10. So we'll meet in about 5 minutes time. Kaveri has sent the link. Okay, thank you, everybody.